I hope those demo videos piqued your interest about today's topic. One reason I really like this chapter on gases is not just because I like the math, because I like the math. I think the math is a lot of fun to do. And some of you I know don't like math so much, but I like the math. But I also really like doing the demonstrations, and so I'm really kind of bummed that I cannot do some of these demonstrations with you because the crushing the pop can is probably one of my favorites to do. So I'm really kind of disappointed that I don't get to do that. But you know, the really cool thing is you watch the video, you can do that. You can go and do that demonstration, and after we talk today, you'll even be able to explain it to your family. So go ahead and do that. Do that demonstration and for your family and tell them what is going on. So we're moving into section 2B on the gas laws. And before we completely jump into those, we have to get some terminology out of the way. And that's in section 10.5, and that's standard conditions. A lot of times when we talk about the gas laws, we talk about standard temperature and pressure, STP for short. And whenever I talk about STP, the standard temperature is 0 degrees Celsius or 273 K. And the pressure, standard pressure, is 760 torr, which is the same as 760 millimeters of mercury, or 101,325 pascals, or 1 atmosphere. Remember, those are all equivalent. We just learned how to convert between all of those last time. And the reason we have to have a standard temperature and pressure is for comparison reasons, because temperature and pressure affect the volume of gases greatly. And so it just helps to have this standard so that if you see that an experiment is run under standard conditions, you know what those standard conditions are. 0 degrees Celsius or 273 K or 760 torr, 101,325 pascals, or 1 atmosphere. So let's move on to Boyle's law. And that's what those demonstrations were about. So here, I think you can get all of those. So section 10.6 is about Boyle's law, and Boyle's law compares pressure and volume. We're just looking at pressure and volume. We are keeping temperature constant. And it says the volume of a dry gas is inversely related to the pressure if the temperature is held constant. And remember, we said yesterday this is the case of a syringe. And I have a medicine syringe right here. You may have one of these at your house, and this demonstrates this principle very well. If I pull out the plunger here, and I put my finger on the other end to make this a closed system, and I apply pressure, my pressure is increasing, my volume is decreasing. That is this inverse proportion. If one goes up, the other goes down. Now, when I decrease the pressure by letting up off the plunger, the volume increases just all by itself. So go grab a medicine syringe if you have one and try that out. And if you don't, you're going to be receiving one next work exchange. I'm going to send one home with you because that's what your experiment is going to involve. It's going to involve actually a pretty large syringe. So we see if pressure goes up, volume goes down. When I decrease the pressure, the volume goes up. And so a graph of volume and pressure would look like this. Okay, this is that inverse relationship. So let's talk about the demos for a minute. The one with, we call that apparatus a bell jar. And what they were doing is they were using a vacuum pump to take the air out of the bell jar. So they were creating a vacuum. They were decreasing the pressure on those objects, and because they decrease the pressure on those objects, if we decrease the pressure, the volume goes up. So it was going this way. That's what they were doing with the balloon. Take the pressure off, the balloon gets larger. That's what they were doing with the PEEP. Take the pressure off, it's able to expand, and the shaving cream. So what does this have to do with crushing the can? Well, with the crushing the can, they gave a really good description of what was going on with the water, that it was filling up that space, and then when they put it upside down in the cold water, it condensed and there was less pressure on the inside. But what they didn't really talk about was what that then created was there was higher pressure on the outside. The atmospheric pressure was higher on the outside than on the inside. If you have a higher pressure on the outside, it's going to crush the can. It's going to decrease the volume of the can. So it's the exact opposite of the bell jar. This situation with the can increased the pressure on the outside so that the volume got smaller, where with the bell jar it was decreasing the pressure so the volumes could get larger. So that's the explanation for those. So now go ahead and do that can demonstration for your family. So let's take a look at some of the math now. Mathematically, this relationship can be shown as P times V equals K, K being a constant. Okay, this is a constant. This is a number that does not change. So let's say that number is 1. If this number is 1, that means that pressure is 1 and volume is 1. And so 1 times 1 equals 1. Well, what if I double the pressure? If I double the pressure, in order for K to still be 1, that means I have to decrease the volume by half so that I have 2 times a half equals K. That's why they call it an inverse relationship, because in math we call those inverses. When you have a number like 2 and a number like 1/2, those are inverses. And so that is what's happening with this. If you increase the pressure by 4, you have to decrease the pressure volume by 1/4. Okay, and vice versa. If we decrease the pressure by 1/3, the volume would increase 3 times. So that's what that means. Now, since it is a constant, we can compare 2 different situations. We can compare a pressure and a volume in situation 1 to a pressure and a volume in a situation 2, and they will equal the same constant. So we can come up with this equation, P1V1 equals P2V2. We can actually predict, if we change the pressure or the volume, we can predict what the pressure and the volume will be for the new situation of that same gas. So this can be used to solve problems when pressure or volume change. So let's take a look at that. Let's do that. So I'll give you a second to turn off your video and copy down this problem. Okay, I'm going to get out a highlighter and I'm going to highlight some numbers here. So maybe you'll want to do that too. But in my problem, I have some numbers. The problem says a sample of gas occupies 450 milliliters. That highlighter is terrible. When it is under a pressure of, that's 1.02 atmospheres. That was a little bit better. What volume will it occupy if the pressure is increased to 850 torr? And I am looking for volume. So the first thing I do for these problems is I write down all of my values that are in my problem. I write down P1 and V1. And for V1, I'm starting out with 450 milliliters. For P1, I'm at 1.02 1.02 atmospheres. And then I write down P2 and V2. And over here, I'm trying to find the volume, and they give me the pressure as 850 torr. But, uh-oh, I have a problem. I cannot have two different units for pressure. So I must convert one of these. And I'm going to go ahead and convert P2, mainly because I have more room to do so. And so I know that 760 torr is 1 atmosphere, to convert this to atmospheres. And so when I divide 850 by 760, I get 1.12 atmospheres. Now remember, torr is a pure number, so I'm good there. And also, here, probably 2 significant digits, but I can wait until I'm done with my problem to, I always want to carry through one more significant digit until I'm done. So that's why this number is 3 significant digits right now. So I write down my equation. P1V1 equals P2V2. I plug in my numbers, and P1 is 1.02 atmospheres. V1 is 450 milliliters. Whoops, no, I don't want to do that yet. Equals P2, which is 850 torr, times V2, which I'm trying to find. Oh, wait a minute. I can't write 850 torr. I have to write it in atmospheres, so 1.12 atmospheres. Okay, to solve this problem, I have to divide both sides by 1.12. So I'm going to rewrite this problem. Dividing both sides by 1.12 atmospheres. Cancels out over here. What cancels out over here are the units, so I'm left with milliliters, which is volume, so I'm good. When I do the multiplication and the division here, V2 has a value of 410 milliliters. Now this is where I conserve my significant digits. 450 really only has 2, so I can only have 2 down here. The 0, remember, is not significant because it does not have a decimal after it. Okay, so what I want you to do is take a look at page 257, numbers 3 and 4, and read those over and try to answer them yourselves right now. I'll give you a few seconds and then I will give you the solution to those. Okay, so here are the answers, and I'll explain them in a minute, but I will give you a chance that if you got them right, you can just move on. Okay, so number 3 says, when dealing with gases, why is a standard value for temperature and pressure important? And right here, it allows scientists to make direct comparisons since temperature and pressure affect the volumes of gases significantly, as you saw with the bell jar demo and with the pop can demo. You saw that the volume changed pretty greatly. Okay, now question 4, I'm going to do that for you. So I'll get a clean sheet of paper here. So number 4 says a gas has a volume of 95 milliliters at a pressure of 930 torr. What volume will the gas occupy if the pressure is increased to 970 torr and the temperature remains constant? So the first thing I do is I write down the numbers that I know. I know that pressure 1 is 930 torr. So P1, V1, the first volume is 95 milliliters at 930 torr. They give me P2, which is 970 torr, so they are increasing the pressure. So I would expect what to happen to the volume? Right, I would expect it to decrease. So let's see if that's what happens with the math. So we're trying to find volume 2. So I write down my equation, P1 V1 equals P2 V2. I plug in my numbers. P1 is 930 torr. V1 is 95 milliliters. And that equals 970 torr for P2. And we are trying to find V2. Now, for these proportions, as far as pressure and volume are concerned, it doesn't matter what units we're using as long as the units on each side are the same. My pressure units have to be the same, my volume units have to be the same. If not, I have to convert. So when I solve for V2, I'll rearrange my equation here. Divide both sides by 970 torr. That cancels out over there. So V2 equals, I multiply the top and I get 88,350 now milliliters because torrs cancels, divided by 970. When I do that division, I get 91 milliliters. So yes, we see that inverse relationship working here. If I increase my pressure, my volume goes down. I am going to stop the video here and do the homework problems in a separate video because of time.